Sorry, so late for this keynote talk. But anyway, we'll occupy your lunchtime. But I believe this talk will very attractive because PESPA tried to give us the how to deal with high-dimensional data for the denied fuzzy system, and also do some feature selection and for the classification. Let me just briefly introduce PESPA. PESPA was served the Indian Statistics Institute. It also is just like our academic income. Anyway, he just last year just retired, but again he get the from the INSA. Anyway, the senior scientist also served on the ISI. And PESPA is very hyperactive in the IEEE Computational Intelligence Society, which is shown in the CIS. He was the president for the CIS Society, and also he was the editor-in-chief in the IEEE Translation on Fuzzy Systems. And he also be the IEEE Fellow and the IFSA Fellow and so on. Anyway, he said that I should show work for him and let him have more time and give a talk for us. Yeah, let us a big applause for welcome the first part.
Ni hao. Good morning. First of all, let me beg an apology in advance because in between I have to drink some fluid as I have some problem with my voice. When I go to the doctor, say it's not cancer, and the next thing they say that don't speak. So I'll keep on drinking as and when I need. I would like to thank the organizer of both conferences for inviting me to share some of the things that I'm interested in and will do. And I must acknowledge that a lot of people are involved. You know, students primarily do the work and professor give the talk. And here one of the students, Guangdo Su, who is the main, who is a very smart guy trained in mathematics. So I specifically acknowledge him. And before I proceed further, I just want to mention 2 points. One is that I'll go through a few slides which talks about AI, etc. So please do not make an hypothesis that I do not like AI or I'm against NLP or anything like that. I love them and I'm amazed how rapidly they are progressing. So no scope of misunderstanding, I want to clarify that. And second thing is, you might feel like I'm trying to sell fuzzy systems. That is also not true because my living comes equally from fuzzy systems neural network, and in fact, in some sense, sometimes through evolutionary computation also. Alright, so we are in an exciting era of AI. So every talk should start with AI now because everybody talks about AI. And we have superb successes in many areas. And the question comes, is everything is fine with AI? Definitely fine, because otherwise why should people be after AI? But there may be some little problem here and there, we all know. So if you look at the way particularly the LLM is developing, it seems like people believe in a philosophy, bigger is the better. So bigger architecture, larger number of free parameters, bigger data, if we can do it, we are expected to get a better system. Nobody nowadays thinks of principle of minimum description length or things like that. I asked Gemini to list the top 5 models, large language models, and it gave me GPT-4 and Gemini 1.5 with 3 parameters, 1.8 trillion and 1.6 trillion. Note that these the original companies, they usually don't like to disclose the number of free parameters because this may not look very good. So if people are talking about or people are using systems with 1.8 trillion free parameters, and we know that the fuzzy systems has serious problem when the dimension becomes even 10,000. So does it make really any sense to talk about fuzzy systems or neuro-fuzzy systems in today's scenario with high-dimensional data? When I am talking about high-dimensional data, I will go little more than 100,000 because in my title you have seen that I have emphasized, actually my intention was not to emphasize anything, there is nothing special about 100,000. It sounds really good and probably that was the first time we could cross 100,000, so we emphasized in the title. So I don't know if you have seen this particular graph. This is the usage of ChatGPT when it started in November 22 and then this is up to June 2024. You can see around April 2024 there was a sudden fall from the cliff. I don't know what went wrong and I don't have the latest picture of this. This is a published picture. So something must have gone wrong somewhere. People's expectation changed. Otherwise the user level cannot go down to where they started. This is the point. Pointer is okay. So where they started at the beginning. Now, what about the impact of use of the word artificial intelligence in product? A group of scientists in the Washington State University, this is not very old, this June 2024 publications, they made a study that how if you use in a product description that this product uses artificial intelligence, what happens in its sale. You expect that more people will like to buy it, but it's found just the opposite. If you use in the product, this is a quote from the paper. So if you use AI in the description of the product, people's intention to buy goes down, and if the product has a risk associated with it, then it goes down further. It's kind of emotional trust. So why it is so? So why there is so much of concern about AI-assisted product? Well, I cannot give a precise answer to that, but I will mention about 4 points. There may be many, many more points. One is transparency, other is interpretability, third is explainability, and fourth is trustworthiness. I am going to use the word trustworthiness in a very limited sense and I'll explain. Now, these issues are important for today's talk because what I am going to say or try to establish that for 2, 3, and 4, fuzzy systems can do a very good job. And what I mean by transparency, that is applicable to any system and it can be achieved if the developer is honest. So sometimes there are confusion among the use of these terms. By the word transparency, people sometimes refer to transparent model and things like that. So I want to make it clear what I mean by transparency. So my emphasis here is the openness in the design, development and deployment of the AI system, which means the designer should say what kind of data it has used, should release the code. If it is using, for example, medical data, who has annotated the medical data, did they follow the golden rules, things like that. So those things to me is transparency, and this is very important for the users as well as the regulatory agencies. Almost in every country you will have regulatory agencies for AI. Interpretability is understanding of the inner working of the model at some comprehensible level. What I mean is if you look at a multi-layer perceptron or deep neural network, you know what computation is being done, but we do not know what is its impact is going to be. On the other hand, if you look at a rule-based or if you look at a decision tree, then at every node, if we look at the computation that is being done, we know what it means. So that's what I mean by interpretability. And the related one is explainability. When the system makes a decision, it should be able to give you some kind of justification why it has made the decision. Now for fuzzy systems, I may say at this point that it can easily produce a justification, but they may not be necessarily causal relation. So for example, if you use decision tree, you can just trace the path and you can show the user that these are the conditions that is being satisfied, and that's why the decision has been made. Similarly, for a fuzzy rule-based systems, you can pick up the rule. Of course, we have not discussed what fuzzy rule-based system is. I will come to that soon. And we'll try to find out the rule which provides the maximum support to the data, and then that rule can be given to the user as a possible explanation. Now, trustworthiness, most people use it as a big umbrella to cover everything. In my definition of trustworthiness here is very, very narrow. I want to say that your decision-making system should not go beyond the territory for which it is trained. What I mean is specifically, suppose I have trained the system to distinguish between cow and goat, and then I bring a donkey there. My system should not say it's either a cow or goat, and most of the systems are going to do that. However, whether the decision-making strength is poor or not, but it will make a decision. So your system should be able to say, don't know when under right condition. Now, before going to the fuzzy systems or utility of this, to motivate my talk, I just mention here two different classes of applications. These are real applications. Case one is an AI system which is deployed in US, which decides when a patient comes to the hospital, and the AI system decides who will get the intensive care unit, who will get priority. And unfortunately, this is found to be racially biased. And Tesla's autopilot car, according to 2024 report, it has already killed 13 people and injured 13 crashes, 14 people, and 49 persons injured. I do not know what is the current status of this. Now, these two examples, they form two different classes, in my view. In the first case, once your AI system makes a decision, you can analyze the decision and you can intervene. So it says, okay, this person get intensive care treatment, but you can review the situation and you can override the AI system. But in the second case, you cannot do it because you can only do post-mortem. After the accident has occurred, you can probably find that, okay, there's a white track and it has treated it as a sky and just hit the truck. So for the first families of applications, fuzzy systems could be a good choice. There are other reasons. For example, medical applications, medical diagnoses, etc. There also the fuzzy systems can play a very important role. And we'll see that you can easily make it trustworthy in the sense of not making decisions beyond the territory it is trained. We also should note here that all the problems that we deal with, they are not big data problems. There are some small data problems also. For example, in healthcare, if we try to find out the genetic or non-genetic biomarkers, cancer treatment prognosis, expected survival period, diagnostic rules, we don't have millions of data available in most of the cases. Even in case of industry, I was involved in a small project, so we just started using electric vehicles, and some of the questions they have is that how long the battery life is going to be, and depending on the road conditions and the load in the truck, how long the full battery charge will run. And to solve these problems, you don't have too much data available. So there are problems where fuzzy systems can be more useful. But what is a fuzzy systems or fuzzy rule-based system? What can it do for us? I have mentioned that it can do a lot of things, but I have not given you any specific example. Why it is not popular like neural network? Everybody loves neural network nowadays. And using neural network is much easier than using fuzzy rule-based system. Use of fuzzy rule-based system kind of demands quote-unquote some engineering skill. And what are the major limitations and how we have addressed some of the limitations. So let's first see two examples how fuzzy systems perform without going into the details. So we looked at a cancer diagnostic problem. This is what is called small SRBCTC, small round blue cell tumor. There are 4 kinds of childhood cancers. So when you look at the histology under the microscope, they look very similar. But if you misdiagnose, treatment will be different and the kid is going to die. The child is going to die. So you need to do proper diagnosis. And there is a data set with 2,308 genes, and the number of training samples you can see is highly heterogeneous. One class has 8 and maximum number of samples 23. It's highly imbalanced, and there is a test data also. I think Nature Medicine, the first paper was published in Nature Medicine or Biotechnology. So we tried to use fuzzy rule-based systems to address this problem. Actually, we used a neural network to bring down the number of features significantly, and then used a fuzzy systems to bring it down further. And we came up with 7 genes with just 6 diagnostic rules. And here are 2 rules. The rules are something like, if the 2 genes AF1Q and CDH2 are moderately expressed or moderate to highly expressed, and the other 2 genes FGFR4 and FBT1 are low expressed, then it is neuroblastoma. On the other hand, if EHD1 is very highly expressed and all other 6 are underexpressed, then it is non-Hodgkin lymphoma. Now, what are the advantages of this kind of rules? So such rules are comprehensible, doctors can understand it, doctors can check if there are conflict among the rules, because you have a small set of rules and very few genes are involved, and doctor can check if there are cancer subtypes or stages. Generally, you will see soon that each rule represents a hyperellipsoidal space in the input-output domain, and therefore, if there is a kind of subtype of the cancer, or it could be different stages of the same cancer, it is easy to figure out that. Now, the second example I want to mention here is of manifold learning. This award got the TFS Outstanding Award last year. So if you see these 2 pictures, one is Swiss roll, other is S. They look 3-dimensional, but essentially they are 2-dimensional sheet which are just embedded in a 3-dimensional space. So if you want to pull down into 2-dimension, maintaining the topology of the sheet, then you expect a 2-dimensional sheet like this. Now, this is a more interesting example. Look at the first picture of the dark. So now I rotate this dark by 5 degree, 5 degree, and I generate 72 images. Each image is of size 32 by 32, which means each duck is represented by a vector in 1024. We are going to design a fuzzy system in 1024 dimensional space. That means the rule base will have 1024 antecedents, which is itself is quite high. Now, question is, if I bring down the 72 data points into 2 dimensions, what do you expect to see? How do the 2-dimensional points should look like on a sheet of paper? If you think of a little bit, you will see that the circle is the most unbiased assumption that we can make about this data point. And in fact, fuzzy systems can do that very easily. Isomap fuzzy systems and TSNE, they can pull out this circular shape, but there are others which fails. In the paper, there are many more examples. So manifold learning is quite difficult problem, and this is the first work probably using fuzzy rule-based system. Now, I'll be talking about two kind of, with this assumption that everybody may not be an expert in fuzzy systems, or maybe it may be a little redundant. So there could be, there are actually 3 types of fuzzy systems. I'm interested in 2 kinds here. One is classification system, which I have given you an example to distinguish between cows and goats. Let's say if I write rules like if the weight is high and tail length is long, then it is cow or class 1. I can write a rule if the weight is low and tail length is short, then it is goat, it's class 2. So these are classification type of rules. You can ask who is going to give me the rules. My answer could be 2. One is the expert can give the rules, but for most problems, expert will not be able to give you the rules. The other is you can extract them from data using a very, very rudimentary principle. The second one, the antecedent part remains the same, and this model is going to play a very important role in what we are going to discuss today. It's called TSK or Takagi-Sugeno-Kang model, where the antecedent parts remain the same, while the consequences are, I show here a linear function of the input variables, but it could be linear, it could be non-linear, it could be a single term, and still you can show that it has universal approximation property. We skip the Mamdani model, which was the first model used in control, of course, where the consequent is a fuzzy set. Now I said, how are you going to generate the rules? Let's say we have this problem of distinguishing between cows and goats, and I measure the weights and tail length of several cows and goats, and I get these nice pictures like this. So I have got two clusters, and each cluster has a centroid. Let's call them V1, V2. They are vectors in 2 dimensions. And every cow and goat, when it comes, we'll just measure its weight and tail length. So the first cluster cow I can represent is using a fuzzy set called X is close to V1. X is a 2-dimensional vector, V1 is a 2-dimensional vector, and I can use a Gaussian membership functions. You can use complicated triangular, you can rotate a triangle and create it, but Gaussian is easy to understand. And I can define a rule if X is close to V1, then it is a cow. You might be wondering, will it work? Actually, it works great. Similarly, I can define a rule if X is close to V2, then it's a goat. So what is the take-home message from here? If we cluster the data, and if there are nice clusters, each cluster can be represented using a rule, and the rule with the maximum firing strength will decide the class. Now, yesterday's lecture, Professor Lee mentioned that it gives a natural way of transferring knowledge. Now you can see these clusters here. If you get an unknown point, if it falls into the cow cluster, it goes to cow, otherwise it goes to goat. Now, this example is in 2 dimensions. It's easy to visualize using Gaussian memberships. But if it is in 1024 dimension or if it is in 100,000 dimension, interpretation of the rule becomes almost impossible. So we can write down the rules into small lower antecedent clauses for each input variable. Like X has 2 components, X1, X2. The centroid has 2 components, V1, V2. So we can say X1 is close to V1 and X2 is close to V2. Then something happens. And then you see that these clauses are connected by and this AND operation is going to kill our life. So I want to emphasize your attention, draw your attention to this. This AND is typically realized by T norm, and most commonly what we use is minimum or product. Now T norm has a unique property, and this property we have to use, that if one of the argument is 1, the output is the other argument. So therefore 1 does not affect the output of the T norm. And of course the rule with maximum firing strength defines the class. At this point I should make it clear that the way I have translated the rule, these two rules are exactly the same if we are using Gaussian membership function and product for computing the firing strength, but otherwise they are similar, but they are not equal. They are equivalent, but they are not equal. Only in case of Gaussian, and when you use the product, they are exactly the same. So what are the issues? I said at the beginning only, I mentioned about that the fuzzy systems with high dimensional data, it has some serious problems. So what are the issues? So let's consider multi-dimensional input and meso system, multi-input single output system. So my input is in D dimension and output is just 1 dimensional. This is for simplicity. Your output can be Q dimensional also. So the rule, again using a similar previous analogy, I can say if X is close to Vi, then Yi is a linear combination of the inputs. But then X is close to Vi, it is in D dimension, so I just split into atomic clauses. So the first component of X is close to the first component of the V1, Vi, the second component of X is close to the second component of Vi, and so on. And then for each component, I find out to what extent the current input satisfies the antecedent clause. And that's say alpha I1, alpha I2 and alpha ID. And then we have to combine this to get the firing strength of the rule. As I mentioned, there are infinite families of T nodes that you can use, but here we will be focusing on minimum and product because these two are the most commonly used firing strength computation rule. So this is the product of this and then what the output is. So every rule has a firing strength and every rule has a consequence. You make a convex combination using the firing strength. As simple as that. Now this whole system can be realized using a neural network, or you can call it a neurofuzzy systems. This looks fairly complex. Actually it is not complex. I don't want to spend time on this. If anybody is interested, there are associated papers, you can see. But exactly the same thing can be realized using an architecture like this. And once you have an architecture like this, you can use backpropagation type of learning rules, which makes life easier. And you know the inventor of this neurofuzzy system is Professor Lin. The first paper came in transaction computer when nobody else thought about it. So he is really he is pioneer in many areas, but this is one of the areas. Now, I already mentioned there are two commonly used T norms that we use. One is product and minimum. So if we use product, since every component lies between 0 and 1, as the dimension increases, you know that the product, if there are 1,000 values or 10,000 values and every value is 0.9, if you take the product, it goes to 0. And the rule becomes invalid. Sometimes it becomes underflow. So this is a serious problem with high dimensional data, and that's why you don't see much papers which uses very high dimensional data for exploiting fuzzy constants. And minimum is another one which often we use, but problem with minimum is it's not differentiable. If it is not differentiable for a complex fuzzy systems, how do we train the system? We need to use gradient descent and stuff like that. So we need a differentiable T-norm. So often we use a softer version of this T-norm, but you will see that the softer version has also two problems. We have used earlier, and but we figured out that it also has a problem unless you choose appropriate values of Q. Typically Q goes to minus infinity, you can show it gives you minimum, but nobody uses minus infinity because to avoid numerical issues, we use minus 11, minus 12, and it works reasonably well. Does it? Actually, we'll show that it creates problem. Alright, so let's take an example. So I said that this use of soft version of mean, unless you use appropriate values of Q, you may be in trouble. So here is an example. We consider Q is minus 12. I have these three values, and I want to find out the soft mean. You know the minimum is the first value is the minimum value. Now if you raise it to the power minus 12, what happens is you get something like 10 to the power 312, which gives you overflow. So you are in trouble. So this is one kind of trouble. Then the other kind of trouble comes. Here is another example. We have 4 values. We want to find out the soft version of the minimum. Using again Q is minus 2. And we get 4.4977, which is closest to 0.5, but the minimum is 0.48. So 0.5 is the third minimum. So we call it fake minimum. So there are two serious issues. So how can we address this problem? First point is we should use as small as possible Q so that we can get a better approximation to minimum. But the issue is for every rule and every data point, this could be different. So what we have to do, we have to devise a mechanism where the system adaptively find out the optimal choice, quote unquote optimal choice of Q. So if you have 10 rules and you have 10,000 data points, so 10 times 10,000 values of Q you will compute when you are finding the firing strength. So how do you do that? Well, we have this, you can see a formula there. Q hat is 690 by log of minimum of the individual components. How do we get it? Does it come from our head or hat? Well, no. It's, let's say, choose Q. We have to choose Q so that the mu to the power Q is less than equal to the largest number that your system can represent. So that you can avoid overflow. This is very simple arithmetic, and this kid is so smart, he found it. And then you do a little bit of algebraic steps. So what you want, Q should be greater than or equal to 690 by log mu d, and it should be satisfied for all d and for all rules. And therefore, since it has to be satisfied for each antecedent components, so if you take the minimum, then it will be satisfied for all of them. So it's a very simple rule and very effective. So if we go back to the previous example, and for the first example, Q turns out to be minus 11 instead of minus 12. Minus 12 gave us a big problem, overflow, and minus 11 gave us a minimum which is very close to the true minimum. Whereas if you go to the second example, the Q had turns out to be minus 940. See how adaptive it is depending on the data condition, and the minimum you get is very close to the true minimum. But so we address two problems, but this does not solve all the issues with fuzzy systems. First of all, if you have large number of rules, then this is no good. And secondly, if each rule has 10,000 variables or 100,000 variables, are you going to buy it? It's no good, right? So we have to reduce the number of linguistic variables in each rule, and we have to also reduce the number of rules. Now there is a significant amount of literature where we have used the concept of gates or doors to eliminate the linguistic variables. There are many more papers in this area. Now what essentially we do, the feature rejection philosophy. So let's say we have two features x and y, and you have defined two fuzzy sets, three fuzzy sets on each. It doesn't have to be three. It doesn't have to be same for all variables. Now we set a mathematical model of door, and this variable x, y goes through the door. The door initially is kept little open, and if this variable can help you solve the problem, then the door will be open. If this variable cannot solve you the problem, the door will be closed. Now question is, what is meant, door will be open is easy because everything goes unaltered inside. But what is meant by closing the door? Now for each variable, linguistic variable, you have number of fuzzy sets. So what you have to do is, you have to deactivate all of these fuzzy sets so that they don't have any impact on the output. Initially, you may think this is not possible, but with a very simple concept, it's possible. So what we do, we define door as, say, m lambda I, where lambda is the door opening parameter, and it is defined as e to the power minus lambda I squared. And then how do we change the membership values? As it goes through the gate, if the actual membership value is z, then we raise it to the power the gate value. Now watch it carefully. If lambda equal to 0, then e to the power that quantity becomes 1, and the membership remains unaltered. And if it is plus minus infinity, then what will happen? Z to the power 0, and it will make the membership value 1. And we know that for t norm, one membership value does not affect the output. So the goal would be, for good feature, somehow make lambda x close to 0, and for bad feature, somehow make lambda y close to plus minus infinity. Now, how can you do it? Well, it's easy. I said that initially you keep the gate little open, and now you can use gradient descent to tune the parameter lambdas of the gate, and then you can select bad features and good features. But here, watch, the doors are used at the level of antecedent. More recently, what we have done is we have used doors at the level of consequence, and it makes us easy to select rules as well as select the features. In fact, you will see that from 100,000 you can, but at least 7,000 you can bring down the number of features to 30, 40 and get a very good fuzzy systems. So these are some of the common choices of get function. Recently we suggested this one, and there is a reason behind it. Because all the top first three, they have a problem. When the get value becomes 0, their learning rate becomes very slow, because the derivative becomes very slow. And that would be very clear. These are messy pictures. Just look at the blue picture only. On the left side, the gate opening, closing. On the right side, we have the gradient. And you can see for the blue, at 0, the gradient is quite steep. So when your learning comes close to 0, then you very rapidly learn it. But in our case, in the previous door models, like the first three, it becomes very slow. So that becomes a problem in learning. So what we do is to design the system, you can initialize the system in many ways. We have used a very simple scheme. You take the domain of every feature and split into, say, S number of uniformly spaced interval, and you set one Gaussian membership for each of them. Don't worry about this. Training starts with 2D plus 1 S types number of fuzzy rules. This is slightly tricky scheme. For details, if anybody is interested, you can look at the paper. But let's say you start with some number of rules. Now there are three tasks at hand. One is feature selection, second is rule selection, and final is refinement of the rules. So unlike the previous cases, as I mentioned already, that this time I am going to use the gate at the level of consequence, both for feature selection as well as for rule selection. So if you consider the rules, say consider one rule Ri, where x1 is close to vi1, x2 is close to vi2, etc., then you have the consequent. So what we do is, we have one get for one linguistic variable, and we multiply, you see xj is multiplied by the gate opening. And initially the gate is open very little, and when you learn the system, the gate will be closed depending on the needs. If it is useful, the gate will be open, and if it is not useful, the gate will be closed. And if you want to select rules, then you have to apply the gate at the level of rules. So here you can see that m theta I, for each rule there is one tunable parameter. Again, at the beginning, you make the rule almost inactive, don't make it completely inactive, then the learning may not proceed. So you choose theta in such a manner that the rules are a little bit of active, and then you use gradient descent. You can of course use some other schemes also, but we used gradient descent primarily because this is consistent with the way we want to open the gates and close the gate. Now, how does it work? There are a lot of results in the paper. Now, here you have some 19 data sets, of which 7 are reasonably high dimensional data for fuzzy systems. The last two are more than 7,000, more than 7,000 dimension. If you look at this, we compared with some existing system also, and we can see that within bracket we have the number of features that we have used and the number of rules. Now look at some of this high dimensional data. The high dimension comes in the next slide. This is the low dimensional data. Here, of course, most of the cases the proposed system is doing better performance. Maybe I can skip, and high dimensional data are more interesting. Look at the last three data sets where the dimensions are For fuzzy systems, it's quite high. And for the Liquidia datasets, it selected 11 features and created only 4 rules for the classification. So which is pretty good, from 7,000 and coming down to 11 and starting with a large number of rules to 4 rules. That's pretty good in our view. This is some benchmark method that we compared with. So now, did we address all the issues of fuzzy systems with this? The answer is certainly not no. My title says 100,000, crossing the barrier of 100,000 variable. And here we have gone only up to 7,000 plus dimension. So what happens with 100,000 plus, and what happens if we use product inner, which we have raised as a problem but we did not address it. We shall try to address this issue now. Alright, as usual again, so your input is in D dimension, and consider just one antecedent, atomic antecedent clause, like some x1 is close to xd is close to md, and we use a Gaussian membership function as shown here. So if there are d, then we can compute the firing strength using the product. It's easy, and from there what you can do is you can simplify the firing strength, the e to the power minus summation of this xd minus md by 2 sigma d squared. Now let's say the smallest positive number that the computer we are using, it can represent as e to the power minus xi. Then in that case, if I want to avoid underflow, my firing strength must be greater than equal to e to the power minus xi for all rules, for all cases. So that gives me that this term in the e to the power that must be less than equal to xi. Now, but this is not useful because here we have to make some simplifying assumption. So let's say instead of using different sigma for different antecedent, atomic antecedent clause, let's say same sigma. We'll change it later. So we use the same sigma, so then what do we get? We also assume that the data are normalized to 0, 1, which is very common in fuzzy systems, because if you do that, then you are in a better position to interpret the rule. And we also assume that every centroid of every Gaussian lies between 0 and 1. Why do I say so? Because sometimes if you use gradient descent, it can cross the boundary, but if it crosses the boundary, we'll set it to the boundary. Now this is a condition which we are going to exploit. So therefore this x minus md absolute value will be less than equal to 1. So the square of that will be less than equal to 1. If that is the case, so with these two conditions, we finally end up with a condition that 1 by sigma, which is the spread of an atomic antecedent clause, is less than equal to xi by capital T. Capital T is the dimension of the data. So if this condition is satisfied, then of course you will never get underflow. But is it any good? This is a feasible solution to avoid underflow. If we use sigma equal to capital D, it's a feasible solution to avoid underflow. But this will give, suppose in 100,000 dimension, if your spread is 100,000, then you get a flat membership function, and the specificity of the rule completely goes out. So this is no good. So the rules will have very low specificity. So what we do is, let's see if we can reduce it further. So we assume sigma is d to the power rho, where rho belongs to r. Actually it lies between 0 and 1. If it goes beyond 1, then your spread will be higher. And then you can, using this again little algebra, you can find out the lower bound of rho is 1 minus log xi by log d. So if you use this, you can get the maximum specificity of the rule and you will never get underflow. you will never get underflow and the maximum possible specificity of the rule. And this bound is for Gaussian membership function. We have in the paper for triangular and trapezoidal membership functions also. Now a 64-bit processor can represent roughly the smallest number is e to the power minus 745. So xi is 745. Then if you compute the rho hat, then it becomes, even for 100,000, it's less than 0.5. So therefore you can reduce the spread of the Gaussian significantly. So then if you satisfy three conditions, one is that the rho must be greater than or equal to this lower bound, features are normalized to 0, 1, and center of every Gaussian lies between 0 and 1, then d to the power rho hat will give you a fuzzy system which is safe and maximum possible specificity. But will you be happy with this? Because with every rule, every antecedent, you have the same spread. So this is no good. So what we do is, to avoid this, we add a small quantity sigma RD square, which can vary for every rule and every antecedent clause. And since we are adding a positive quantity, we'll never encounter overflow, and we can tune this sigma RD. So how does it perform? Okay, so here you can see again 14 plus 4 data sets. 14 is classification and the last 4 are treated as regression problem. For the last 2 data sets, you have 100,000 dimension and more than 120,000 dimension. Similarly for the 2 regression problems, there are enough results in the paper. Now here we compare with the product TSK, that means if we use directly product, adaptive TSK, the one we have proposed already. ALE TSK is another one proposed by the same group, but I am not involved with this. And HT TSK is proposed by Professor Dongru Yu, who is going to give a talk tomorrow. And the last one is the current method. Now if you look at the results, the performance is quite good even in such high dimension. But note that in this process we have not reduced the number of features, number of linguistic values, but we have tools to do that. And for the regression model, if we also do, then we can see that out of 4 cases, 3 cases it performs better. And there are the references to those work that we have compared with. So the third issue, here you have a room with 100,000 dimension. Are you going to happy with this? Well, you should not be, but I have already discussed a method to reduce the number of linguistic variables as well as the number of rules. So you can use similar things to reduce the number of rules now. So going back, we started that fuzzy systems will give you an explainable system. Well, you analyze the rule with the maximum firing strength, and obviously that is understandable by the human being. It's interpretable because if you rule is written in a kind of natural language and you know exactly what is being done at every rule, so you understand what is being computed there. Less likely to make poor generalization. This is very, very important. If you remember the example of the cluster, I converted every cluster into a rule. So you can see that one rule represents a hyperellipsoidal space in the input-output space. So therefore, and the rule essentially computes some kind of similarity to the centroid of this hyperellipsoid. So you are very unlikely to make poor generalization. Now you might ask a question, if the data do not have any cluster, what will happen? Will the system work? Actually it works. I have other slides on that. You can impose artificially structured cluster and the system works equally well. Oops. No, I wanted to go back. Alright. The next is, it's easy to make trustworthy in the sense I have said, don't go beyond the territory we have trained you for. Now, it can say don't know if no rule is fired. If you use triangular membership, there could be cases where no rule is fired, but with Gaussian membership, always some rule will be fired with a very small, maybe 10 to the power minus 100 or 5 instance. So you can threshold it and say that don't make a decision. If the second maximum firing strength is very close to the max, and the max is reasonable, then you can say it's a multi-class scenario or there's a confusion. So, few concluding remarks. For some problems, fuzzy systems can be more useful or better. Not for all problems, I must mention that. It can help in knowledge discovery. We have seen that, like, we process satellite images, there were 14 classes and we got 15 clusters. We analyzed the 2 clusters for a particular class and we realized that there were some differences, although they were one kind of objects, but there were significant differences between the 2. And similarly for gene expression data, like 2 rules maybe for one particular disease, and if you analyze in details, you may be able to find subtypes. So this kind of knowledge discovery can happen. Now our method guarantees avoidance of underflow, overflow, effect minimum, but the specificity of the rules still may be very low for the second method at least. So for very high dimensional data, still it needs improvement. But what we can do is, once we get the rule base which works, we use one of our earlier methods to reduce the number of features, number of rules, and then once we do that, we can define the memberships easily and get more specificity. Now, people talk about fuzzy systems model ambiguity. Most of the time they don't talk about specificity, but this is also a very important point of this. Alternate avenues may be possible to address high dimensional data, and there is one problem. If we have really a data set with large number of maybe 1 million instances of data, now if we try to design fuzzy systems using the philosophy that I just mentioned, use of clustering, etc., we may have problem. We may end up too many rules, which may not be needed. So need some investigation. Thank you.
Anyone with question for Vespa?
Yeah, Professor, I really appreciate a very exciting talk, especially you address the very important problem about the fuzzy logic, about the high dimension issue. Yeah, I think that can promote the fuzzy logic to the next important milestone.
Yeah, that's what we hope also, because people gave up on it.
Okay. I just some technical question. The first question always in my mind, since I heard about your presentation before, and also this research, and also my team also worked on this. So it seems that the underflow, overflow, always a very important issue, right, for the high dimension input for fuzzy logic system. I'm just curious, is there any specific reason? For example, when we talk about the neural network, deep neural network also quite high dimension, but it seems that the less people concerned about this. So is this the problem specific to the fuzzy logic?
I would say this is a problem very specific to the use of T-norm. For example, if we use average as a firing strength, and I'm sure that tuning will give us a rule base to work with, but the way we interpret fuzzy rules, that will be lost, because we are, instead of using AND, we are using an aggregation operator, say average. So this is because of the use of T-norm. If we use product, even if every antecedent clause has a degree of satisfaction, say 0.9, and if we have 100,000, so the firing strength becomes 0.9 raised to the power 100,000. So we are surely going to get underflow. This is very specific to fuzzy system because of the use of T-norm.
Very great. the other issue is a bigger problem. Since as a godfather of the fuzzy logic, that you already addressed the important issue of fuzzy logic. And so we are always, in our fuzzy society, we always consider how when we can beat the deep neural network. And then it becomes so popular right now. Yeah, so I mean, they already can address a big.
Yeah. This is a very good question, and this question is related to the last point that I have mentioned. Because typically, in case of deep neural network learning, etc., we deal with large, huge data sets because you have too many free parameters, etc. But we have not done, you see the last point in my slide was that if the data set has large number of instances, then how do we deal with it? Well, in principle, we can get a very big rule base, but from fuzzy set theory point of view, I don't know whether it is useful or not, but we can try now. Now we have reached 100,000 dimension. We hopefully can reduce the number of features in this set of rules using our previous method, and then we may try to consider some of the problems because you have seen that 1024 dimensional image we have used as an input, and we have projected in 2 dimension, and it could beat many classical famous methods. So we can try that, but yes, we have not. Large number of instances is an issue. I don't know how, because it may lead to many more rules, tuning, etc. Unless we deal with, it's difficult to say very specifically, but the same question I have in mind, that's why I raised this point, that probably if we take a very large data set and try to solve the problem, dimensionally to some extent we have addressed up to 124 dimensions, so 124,000, which is very big for many applications.
Thank you very much.
Thank you.
It's time limit. Time limit, and I think all of that should be feel hungry. So should be end of this.
I'm sorry I kept you busy here.
Anyway, there is a single perspective.
Wait a moment. Yeah. So I would like to take this opportunity to thank Professor Pal, and I want to share one experience, a memory to you. Okay, around 22 years ago, so Professor C.T. Lin, he first time invited Professor Pal in NCTU, National Jiao Tong University, in this conference. So that is 22 or 23 years ago. 23 years ago. Yeah, so I would like to take this opportunity to invite Professor, our NCTU lifetime distinguished Professor C.T. Lin to give this souvenir and also the appreciation to Professor Pal. Yeah, let's give a big hand to this. Okay, so it's our lunch time, so we also already reserved a lunch box. Don't worry about your lunch. Okay, so enjoy your lunch right now. Thank you. Thank you.